Okay, congratulations everybody, you made it through DP. We're past the DP section of the course, and you don't have to think too hard about DP anymore until the final exam. And so now what we're going to do is we're going to move into another unit of the course called greedy methods. So we've already thought a little bit about greedy methods, right? So you have kind of an intuitive idea of what they are. We're going to formalize that a little bit here and kind of define what we mean by greedy methods. But before we do that, let's just think about what we've seen greedy methods accomplish in the past. Right, so we have already, and I shouldn't say used, I should say we've already attempted greedy methods on at least two problems. So the first was the knapsack. Right, so in one of the early homeworks, you were supposed to implement an exhaustive search algorithm for the 0-1 knapsack, and also a greedy algorithm. And you were going to do a particular greedy algorithm that ranked the items by their value and then picked the most valuable first and went on down the list. And what did we find? We found that the greedy algorithm was not guaranteed to find the right answer for the knapsack problem. Right? So the greedy algorithm, let's say, failed in this case to give us the correct answer. Right? It would always give us an answer, but that answer wasn't guaranteed to be correct. So the other one we tried was coin change. So for coin change, we found that for some sets of denominations, perhaps not all, but for some sets of denominations, the greedy algorithm that basically says take as many of the most valuable coin that fits, then go down the list, we found that algorithm failed as well. So I should say fail. And let's just be very specific here and say it failed for some denominations. Right, maybe not for all denominations. And there's a question on your homework that addresses this and asks you to think about what it would make to create a set of denominations where a greedy algorithm would actually work. Right, but so far, greedy doesn't look very good. Right, it looks like greedy algorithms have serious problems. Okay, so far, issues. Okay, but it turns out that there's actually some problems where greedy methods surprisingly can give you both fast and optimal answers. So before we get into what kinds of problems greedy methods work for, let's just define greedy. So what is a greedy algorithm? So technically speaking, a greedy algorithm, it has to be for an optimization problem. So most of the problems we look at here are going to have some optimization flavor. It's going to be something like maximize the value of a solution subject to some constraints. And so what a greedy algorithm does like this. So as any algorithm that we look at in this class, it builds up a solution to the problem in steps. So let me just say greedy algorithm. So it builds the solution in steps. We'll see this as kind of a repeated thing over and over again. We'll see that the greedy algorithms they build a solution by adding stuff to the solution over time. So it builds a solution in steps. Okay, so at each step we do three things. So each step where we add something satisfies essentially these three properties. Okay, so at each step we have this. And I'll say we make a choice that is one, feasible. Okay, so this is sort of the obvious piece. We're not allowed to, for example, if we're thinking about this in terms of the knapsack problem, we're not allowed to add something to the knapsack that doesn't fit in the knapsack, right? So it has to obey the rules or satisfy the constraints of the problem. Problem constraints. And I'll say, e.g., for example, can't overflow the knapsack. Okay. So 2, every choice we make at every step is irrevocable. And so this isn't maybe something that you would have initially thought of, but this is kind of fundamental to what makes greedy algorithms greedy. So each choice is irrevocable, which means we can't take it back. So when I add something to the knapsack, in a greedy version of the knapsack, I'm not allowed to go back and reevaluate whether that was a good choice. Okay? So this irrevocability is one of the key things that differentiates a greedy algorithm from a DP algorithm. In DP algorithms, we also always add things that are feasible, at least in sort of a generalized sense. If we're thinking about comparing it to greedy algorithms, we always maintain feasibility, but we also always keep our options open in a DP method, whereas in a greedy method, we don't. We say, as soon as it's in the knapsack, I am not going to go back to revise my choice. Okay, so for example, if in the knapsack, once I add it, it's there. In the coin change, once I've selected a coin, it's selected, and I can't go back and say, oops, that one didn't fit, let me repack that coin. Okay, so can't revise choice later. And for example, can't remove something already added to the knapsack. And you can think of this as a key thing that differentiates greedy from DP. And then 3, and this is what really makes it greedy. Like the other two are necessary, but what really makes it greedy is that the choice has to be locally optimal. Okay, so that's a fancy way of saying it does the best we can in one step. Okay, so what does locally optimal do? Well, in terms of like a greedy algorithm for the knapsack, the idea is we imagine that we're only allowed to add one more item to the knapsack. And so what does the greedy algorithm do? Well, among the items that fit in the remaining space in the knapsack, it adds the most valuable one. Right? That's the greedy algorithm for the knapsack that we were thinking about before. That's how it works. Right? At every step, the algorithm makes this sort of implicit assumption that the world is ending after this step. So it tries to do the very best it can to get the most value it possibly can in that one step. The exact way that locally optimal works out is going to be a little bit different from greedy algorithm to greedy algorithm. And in fact, there's a different greedy algorithm for the knapsack that doesn't exactly work according to that exact same principle, but nevertheless, you get the idea. The algorithm essentially pretends that the world ends after this step, and so it tries to do as good as it possibly can in this next step. So basically, let's just be informal and say, pretend the world ends after the next step. So this is your last chance to get as close to the correct answer as possible. So this step had better be as good as possible. And you could phrase this in terms of like, how, what's the difference between the value of the objective function at this step versus versus next step, and you want to maximize that difference, right? You want to increase your objective value as much as possible in this step. But exactly what this looks like varies a little bit from problem to problem, so we're gonna leave it at this. With some things it'll be obvious, like with the coin change problem, locally optimal means you put the largest coin in your pile of change that you possibly can. Right? You take the biggest step forward that you can. Okay, so far greed hasn't been that good, right? It hasn't given us good solutions, but it turns out that that's not a general fact, right? Sometimes we do have this reality that greed is good, to borrow Gordon Gekko's phrase. So sometimes things are fine. And so this unit of the course is going to be all focused on understanding when this is the case. And so we'll spend the next maybe 4 lectures basically asking this question: when is greed good in an algorithmic sense?